Launch director.
Launch vehicle is ready to launch.
We have
Mr.
ignition.
Director, you have permission to
2,
launch.
1, and liftoff. Liftoff of the United Launch Alliance Atlas V rocket.
Mach 1, execute, and we have indication of spacecraft separation.
At Space Launch
Alliance Atlas V rocket.
Mach 1, execute, and we have indication of spacecraft separation.
Space Launch At Space Launch Complex 41, an Atlas V rocket is fueled and ready to launch AEHF-6, the sixth advanced extremely high-frequency satellite for the Space Force's Space and Missile Systems Center. Good afternoon and welcome to Cape Canaveral Air Force Station in Florida. I'm Amanda Sterling and I am the Program Operations Lead on the Vulcan Centaur program. The launch team is not working any issues at this time and we are proceeding towards a liftoff at 2:57 p.m. Eastern Time. A few seconds from now, the count will enter a planned 15-minute hold. There are 2 planned holds in our nearly 7-hour launch count. The planned holds give our team additional time to resolve any issues prior to entering the terminal count. Will Ulrich, the 45th Space Wing's weather officer, recently briefed the launch team on current weather conditions here at Cape Canaveral. The probability of violating launch constraints is 10%. The ground winds are 5 to 10 knots out of the northeast, and the temperature is 77 degrees Fahrenheit. So the weather is within the launch commit criteria and looks favorable for the planned T0 of 2:57 p.m. Eastern. Because of the long duration of today's mission, live coverage will conclude following the separation of TDO-2, a 12-unit CubeSat attached to the Atlas V aft bulkhead. Following today's broadcast, check out ULA's live launch updates blog at ulalaunch.com, where you will find official and timely information regarding the AEHF-6 mission. Now, let's take a look at all of the events from liftoff through AEHF-6 separation.
And liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine and 5 solid rocket boosters ignite to lift the rocket away from the pad. Together, the main engine and 5 SRBs generate a combined liftoff thrust of 11.5 million newtons, or 2.6 million pounds. Shortly after liftoff, Atlas begins a pitchover to attain the proper flight path, while minimizing the pressure the vehicle experiences during flight. The Atlas V reaches Mach 1, the speed of sound, at 35 seconds. The first 2 SRBs are jettisoned at 1 minute 47 seconds, followed a second and a half later by the remaining 3 SRBs. Approaching payload fairing jettison, the Atlas V is burning propellant at a rate of 907 kilograms, or 2,000 pounds per second, traveling more than 11,000 kilometers, or 6,900 miles per hour, and located 124 kilometers, or 77 miles in altitude, and 283 kilometers, or 176 miles downrange. During ascent, the spacecraft is protected inside a 5-meter diameter payload fairing. This 2-piece shell encapsulates both the Centaur upper stage and the satellite. At approximately 3 minutes 25 seconds, the vehicle is climbed above the densest part of Earth's atmosphere and the payload fairing is jettisoned. At 4 minutes 26 seconds, propellant levels deplete and the main engine shuts down. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The vehicle now weighs a little more than 5% of what it did at liftoff. At 4 minutes 42 seconds, the first Centaur main engine burn begins, sending the Centaur into a circular orbit. At 11 minutes 47 seconds, cutoff of the Centaur main engine, or MECO-1, occurs. Following an 11-minute coast to an optimized longitude to allow for proper alignment of the second burn to geosynchronous transfer orbit, the Centaur main engine is restarted for the second of 3 engine burns. A little more than 6 minutes later, second cutoff of the Centaur main engine occurs. At 29 minutes 24 seconds, a payload attached to the Centaur's aft bulkhead separates. This 12U CubeSat is provided by the Space Force and designed to test new capabilities of small satellites used by U.S. government agencies. Following separation, the mission enters a more than 5-hour coast phase. This ultra-long coast is made possible by the addition of an extended mission kit. The kit outfits the Centaur with the extra batteries and insulation required to survive the long trip to apogee. Taking AEHF-6 to apogee allows Centaur to perform a final burn to raise the spacecraft's perigee. At 5 hours 36 minutes, the main engine ignites for a third and final burn. A minute and a half later, Centaur completes its final engine cutoff, following total fuel depletion. Also known as minimum residual shutdown, this capability maximizes the energy AEHF-6 receives to orbit, taking it farther than a guidance-controlled shutdown and ultimately increasing the lifespan of the satellite. At 5 hours 40 minutes 57 seconds, Centaur releases AEHF-6 on its mission to provide communications for high-priority military, ground, sea, and air assets. This Atlas V flight is the first mission for the United States Space Force.
SCLC, Net 1.
This is SC.
Verify spacecraft is on internal power.
Spacecraft on internal power.
ULA is using the Atlas V 551 configuration to launch AEHF-6. This is the 83rd flight of the Atlas V rocket and ULA's 138th mission. Produced in ULA's 1.6 million square foot factory in Decatur, Alabama, the 551 is the largest and most powerful configuration in the Atlas V fleet. It is comprised of a common core booster powered by an RD-180 engine, 5 Aerojet Rocketdyne solid rocket boosters, and a Centaur second stage powered by an Aerojet Rocketdyne RL-10C1 engine. Events that took place in preparation for today's launch began February 27th when the satellite was encapsulated inside the payload fairing. The RUOG 5-meter diameter payload fairing protects the AEHF-6 payload during ascent. On March 11th, the encapsulated payload was transported to the Vertical Integration Facility, or VIF, at Space Launch Complex 41, where it was mated to the Atlas V rocket. The launch countdown begins with moving the rocket from the VIF to the pad. At approximately 11 a.m. Wednesday, the quarter-mile trip began using 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the Mobile Launch Platform, or MLP, supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and the rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the portable environmental control system provides air conditioning to the payload and rocket. Finally, trackmobiles provide the power to move the 3.5 million pound convoy. A third trackmobile is added to the front of the convoy to move our largest Atlas V configurations like today's 551 rocket. The Atlas V rocket stands about 60 meters or 20 stories tall and weighs about 580,000 kilograms or 1.3 million pounds fully fueled. The RD-180 main engine and 5 solid rocket boosters produce nearly 11.5 million newtons, or about 2.6 million pounds of thrust, to lift the rocket off the pad and begin its journey to orbit. As I mentioned earlier, Atlas V is launching the 6th and final satellite in the Space Force's Advanced EHF constellation. Built by Lockheed Martin, the AEHF constellation is the next generation of global, high-security, survivable communications satellites used by all branches of the United States military, national leaders, and international allies. AEHF satellites are the follow-on to the Department of Defense's current 5-satellite Milstar communications constellation. The advanced EHF constellation will consist of 6 cross-linked satellites and is backwards compatible with the Milstar constellation, with a substantial increase in throughput and coverage to users. This increase gives users the ability to transfer information globally in seconds rather than hours. As the world takes on the difficult challenge of slowing the spread of COVID-19, we wanted to take a moment to share how ULA is responding to the situation. ULA is critical to our country's national security and civil exploration missions. This is a role we take very seriously. Part of fulfilling that purpose is safeguarding the health and safety of our employees, visitors, customers, suppliers, and communities. To that end, as we continue operations, we are following guidance from the U.S. Center for Disease Control, as well as state and local guidance in the communities in which ULA has a presence. As an entity designated part of our nation's essential critical infrastructure, ULA continues to fulfill our duty to our country and our fellow citizens.
Also, place SRB ignition SNA switch in the enable position.
The artwork on the payload fairing of today's Atlas V rocket is six-sided to represent the sixth satellite in the AEHF constellation. In the center, there are 5 satellites around the Earth, with the sixth satellite as the prominent feature of design. The program's stakeholders are around the edge, along with each partner country represented by their flag. The Atlas V rocket is also sporting another new piece of artwork, the Space Force seal. This seal represents the newly formed Space Force. Of course, all of you watching today's webcast will have a great view of the liftoff, but those on the southeast coast of the United States and into the Atlantic will have a front row seat. Here's a look at what you'll see. The red line represents the rocket's trajectory, and the time in the upper right corner corresponds with elapsed time from liftoff here at Cape Canaveral. So if the skies are clear, step outside and see if you can see the launch.
L-8 minutes.
LC switch to the ready position. All steps are complete prior to the status check.
We remain in the planned 15-minute built-in hold as we continue to prepare for liftoff. In a few moments, launch conductor Scott Barney will poll the launch team for the final go to pick up the countdown. 29 engineers and managers are polled for system status and readiness to proceed. This is the final status check before launch for all Atlas vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling of the launch team.
L-7 minutes.
Status check to proceed with terminal count. Atlas system. Propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Water. Go. SETAR systems. Propulsion. Go. Pneumatics. Go. LO2.
Go.
LH2.
Go.
HASGAP. Go. Electrical systems. Airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GCQ.
Go.
Operation support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Red line monitor. Go. Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer. Go. Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director. You have permission to launch. Proceeding with the count. ALC, verify T0 is set for 1857. So
Verified.
Polling is complete and the launch team has given the go for launch. From T-minus 4 minutes until launch, you will be listening to Scott Barney and his team performing the final steps in the countdown procedure. You will hear the team call out that Atlas LO2 topping has been secured, followed about a minute later by the call out for transferring the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur LH2 and LO2 topping activity. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed by verification of Centaur tank pressures. A final status check of Atlas, Centaur, and AEHF-6 readiness is conducted at T-minus 25 seconds. At T-minus 3 seconds, the RD-180 engine will roar to life. After liftoff, you'll hear the voice of Jesse Gonzalez providing launch vehicle ascent data. This is Atlas Mission Control at T+4 minutes and holding. We anticipate releasing the hold in just a few moments.
3, 2, 1, mark. 3:55.
Ground pyros enabled.
The countdown clock has resumed, and we are go for launch at 2:57 p.m. Eastern.
T-minus 3 minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
T-minus 2 minutes, 50 seconds.
FTS internal.
T-minus 1 minute, 59 seconds.
Vehicle internal.
1:55.
Launch sequencer start.
1:50.
Securing Centaur LH2.
Securing Centaur LO2.
1:40.
Launch enabled.
1:37.
FTS on.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
T-minus 1 minute, 20 seconds.
OCU's armed. SCO count started.
1:15.
Reduce CCS for launch.
Right.
1:10.
Vent valves locked.
T-minus 1 minute.
T-minus
Range
1
status.
minute.
Range green.
Hold. LC switch not ready. Flight control, got to hold at approximately T-minus 46 seconds. All team, proceed to Operation 80.
Centaur tank venting in progress.
Roger. A recycle call by flight control at T-minus 159. Excuse me, T-minus 46 seconds. LC switch is not ready.
Atlas tank pressures are stable at 30.
Roger.
Centaur tank pressures are stable.
Roger.
Flight control is ready to reset the clock to T-minus 4 and holding.
Roger. ALC, reset countdown clock to T-minus 4 minutes and holding.
Roger.
This is Atlas Mission Control. The team is working to reset the clock to T-minus 4 minutes and holding. We will pass along a new T0 when it's available.
Countdown clock is reset to T-minus 4 minutes and holding.
Roger. OSM, LC.
OSM.
Step 50, place SRB ignition SA switch at disabled position.
SRB ignition disabled.
LC to flight control.
Go flight control.
Yeah, step 30 SS FAPS inactive. That's the S in pre-flight mode.
Roger. All stations recycle systems back to T-minus 4 and holding configuration. Hold occurred at 46 seconds. Report status of completion.
LC Lux 1.
Go Lux 1.
Atlas Elosu topping in progress.
Roger.
Atlas tanks to flight pressure and Atlas pneumatic pressure is stable.
Roger.
LC FTS.
Go FTS.
Step 310, substep Juliet, FTS safety external.
Roger.
And LC step 310, Echo, CEC active, and Foxtrot, Centaur pneumatic system stable.
Roger.
This is Atlas Mission Control. Launch conductor Scott Barney is guiding the launch team through the steps to safe the rocket and pad systems following the unplanned hold called at T-minus 46 seconds. Meanwhile, engineers are examining the cause of the countdown stoppage. We are still sitting at T-minus 4 minutes and holding, and we will pass along a new T0 when it's available.
Substep reset. Substep November, ECS, set point stable.
Roger.
LC locks 2.
Go, Lexi.
For operation step 310, substep golf, Centaur LO2 continuing topping.
Roger.
LC prop 1.
Go.
First substep Charlie, Atlas propulsion system stable.
Roger.
First step Delta, Atlas hydraulic system stable.
Roger.
LC, this flight control.
Go.
Step 310, substep Kilo, flight control ready.
Roger.
Substep Lima, GC cube ready.
Roger.
Step Mike, red line monitor ready.
Roger.
This is Atlas Mission Control. The team is working the activities to save the launch vehicle and the ground support equipment to put the Atlas V and Space Launch Complex 41 back into the same configuration as it was at the T-minus 4-minute hold point. As the team works that, the team is working to determine the issue that initiated the hold. In addition, today's available launch window does extend to 4:57 p.m. Eastern Time.
Has gas, LC, that one.
Go ahead, LC.
Just want to verify you're still completing your has gas readiness.
Affirmative. Just verified. Has gas is ready.
Roger. LD, LC, that one.
LD-L1.
SLD, we did hold it 46 seconds. Recycle of the system is now complete, awaiting completion of the issue that caused us to abort out and waiting on that resolution.
Roger that. Once we hear the resolution, we'll coordinate with the mission director and coordinate a new T0.
Roger.
This is Atlas Mission Control. The recycle of the system to the T-4 minutes and holding point has been completed, and we are just waiting on the resolution of the issue that initiated the hold. The team is continuing to work that, and we will provide updates as we get them. This is Atlas Mission Control. The launch team has completed the countdown recycle of all systems. Engineers are now troubleshooting what caused the countdown to be stopped and how to resolve the issue.
Looking at the data, and we'll get you a response.
Roger. Please convene the anomaly team. Provide recommendation.
We'll go.
While we wait, I want to take a moment to remind viewers of the spectacular work and success our ULA team, Lockheed Martin, and the Space Force have had in launching the first 5 AEHF satellites starting in 2010. Let's take a look at some footage from those launches. Over the last decade, ULA, in partnership with the Space and Missile Systems Center and Lockheed Martin, have orbited the Advanced Extremely High Frequency constellation of satellites, designed to provide secure, protected, and survivable communications. The first satellite launched August 14, 2010 on an Atlas V 531 rocket, followed by AEHF-2 on May 4, 2012, and AEHF-3 on September 18, 2013. On October 17, 2018, the fourth AEHF satellite lifted off on an Atlas V 551. Carrying 2 additional solid rocket boosters, the Atlas V 551 stack provided the additional liftoff thrust required to carry the larger AEHF-4, AEHF-5, which launched on August 8, 2019, and AEHF-6 satellites. With today's launch, ULA's Atlas V and Cape Canaveral's Space Launch Complex 41 close a decade of support to this vital strategic capability. This is Atlas Mission Control. The team is analyzing the data related to the issue that caused the unplanned hold and working to resolve the issue and establish a new T0. This is Atlas Mission Control. The team is working an issue associated with a ground hydraulic accumulator fault. They are working through this issue and will establish a new T0 once we have it resolved. This is Atlas Mission Control. Engineers are continuing to work through troubleshooting steps to better understand the hydraulics issue that has stopped the countdown. The system has been reset at T-minus 4 minutes and holding, and we are waiting for resolution of the issue before we can establish a new T0. This is Atlas Mission Control. The team is continuing to work to resolve the issue with the hydraulics that caused the unplanned hold at T-minus 46 seconds. Once that issue is resolved, we will establish a new T0. We do still have about an hour and a half left in our launch window for today's launch, so we have quite a bit of time left to work through this issue. Today's mission marks Atlas's 665th launch and the 83rd launch of the Atlas V configuration. Let's take a look at the history of Atlas, which first launched in 1957.
And the RD-180 engine roars to life and liftoff of the maiden flight of the Atlas V rocket with a Hotbird 6 spacecraft on board.
As the inaugural flight of the Atlas V lifted off on August 21, 2002, it carried with it the dreams and aspirations of thousands of rocket pioneers who had laid the foundation that made it possible. Atlas V continues the Atlas legacy of innovation and accomplishment that has been vital to our nation for more than half a century. Named after the mighty giant of Greek mythology who carried the world on his shoulders, Atlas was conceived as a weapon and a deterrent, but evolved into a system that pushed the envelope with trailblazing innovation and steadfast reliability. At the request of the Air Force, Charlie Bossert and his San Diego-based engineering team began work on a demanding set of requirements to design an intercontinental ballistic missile capable of delivering a 1,500-pound warhead to a target 5,500 miles away. Their answer, which became known as Atlas, was the top national priority in 1955 as the race with the Soviets engulfed the country. On June 11, 1957, the first Atlas flight lifted off from Space Launch Complex 14 in Cape Canaveral, Florida. The flight ended 38 seconds later, but Bossert's team had taken the first step and proven the structural integrity of their innovative pressure-stabilized steel tank. Complete success for the Air Force and Bossert's team would come just 5 months later, on December 17, 1957.
Go, honey, keep going, baby.
Though the Soviets had beaten the U.S. to space with the launch of Sputnik in October 1957, President Eisenhower would counter a year later when Atlas 10B delivered his holiday message of peace from orbit 180 miles above Earth. Known as Project SCORE, the orbiting Atlas booster became the world's first communication satellite.
This is the President of the United States speaking. Through the marvels of scientific advance, my voice is coming to you from a satellite circling in outer space.
Attention all personnel, report to the blockhouse immediately. Countdown will begin.
On September 9, 1959, Atlas 12D became America's first operational ICBM, following launch from California's Vandenberg Air Force Base. In all, 350 Atlas ICBMs were built and stood on operational alert through 1965. The surplus boosters were refurbished and used by the Air Force, the Army, the Navy, and NASA. The last refurbished booster was launched in 1995. By the early 1960s, the Atlas booster had made the transition from missile to space launch vehicle. 1962 proved to be a pivotal year. Riding atop an Atlas booster in Project Mercury's Friendship 7 capsule, John Glenn became the first American to orbit the Earth on February 20, 1962. Three additional Mercury flights, carrying astronauts Scott Carpenter, Wally Schirra, and Gordon Cooper, set the stage for the Gemini flights and the Apollo missions to the moon. Later that year, Atlas scored another first when Atlas 179D, equipped with an Agena upper stage, lifted off from Space Launch Complex 12 at Cape Canaveral. Its payload, NASA's Mariner 2, became the first successful interplanetary spacecraft. 1962 also marked the debut of the Centaur upper stage, the first to harness the power of liquid hydrogen. The Centaur upper stage, to this day, remains a hallmark of the Atlas system. Together, with its Agena and Centaur upper stages, the Atlas booster went on to play a significant role in America's exploration of the solar system, launching virtually every exploration mission in the 1960s and 1970s.
It was the first spacecraft that was launched from Earth that had enough energy to escape the entire solar system.
During the late 1970s and 1980s, Atlas continued to play important roles in the development of our nation's space program. In addition to building our national security presence in space, converted Atlas boosters also launched the Air Force's Navstar demonstration satellites, leading to the navigation system known today as GPS. In the late 1980s, General Dynamics saw an opportunity to bring commercial payloads back to expendable launch vehicles, and on July 25, 1990, AC-69, the first Atlas I, ushered in a new commercial era for Atlas. The commercial era brought 8 new Atlas configurations over a 14-year span, each carrying an operational payload. The commercial program has enabled breakthroughs in communications, meteorology, broadcast technology, navigation, and national security. In 1995, development of the Atlas III vehicle began. In a bold move, the Atlas booster engine system was replaced with the powerful RD-180, which generates 860,000 pounds of thrust and has throttle capability resulting in a smoother and more efficient ride. Making its debut from Space Launch Complex 36 on May 24, 2000, the Atlas III provided a substantial performance improvement over the Atlas IIAS. Reliability was increased by reducing the number of engines from 8 to 2 and the elimination of 5 staging events, as well as more than 10,000 parts.
This is Atlas Mission Control at T-minus.
In 1998, the Atlas team embarked on a development project for the United States Air Force that would forever change the Atlas vehicle.
And the RD-180 engine roars to life and liftoff with a maiden flight of the Lockheed Martin Atlas V rocket with a Hotbird 6 spacecraft on board for Eutelsat in Paris, France.
For more than 40 years, Atlas vehicles had relied on the pressure-stabilized steel tank developed by Charlie Bossert and his team. In a departure from conventional thinking, the Atlas V development replaced the tank with a structurally stable common core booster. In addition to vehicle modifications, the team took a new approach to processing and launch. Atlas V processing is done vertically, and the mobile service tower has been replaced by a mobile launch platform, which carries the entire assembled vehicle to the launch pad, ready to fuel and launch. The Atlas V is expanded to multiple payload bearing and solid rocket booster configurations, as well as re-establishing a launch capability from the West Coast at Vandenberg Air Force Base. The Atlas vehicle has a long legacy of accomplishment. This record of success, which is nearly unparalleled in the launch industry, is built on the lessons handed down from more than 60 years of Atlas experience. It is also a credit to the dedication and persistence of the Atlas team and their passion for mission success, one launch at a time.
LC Locks 2.
Go Locks 2.
We would like to recommend a transfer line rechill at this time.
Roger. And what is the timing? What's the typical time for that rechill? But you have go to proceed.
Stand by, will advise.
Okay, go ahead and proceed, and just looking for when that would be complete.
Roger. LC Locks 2.
Go.
It'll be about 10 minutes.
Roger.
This is Atlas Mission Control. The team has identified and understands the cause of the hydraulics issue. They are currently working through a solution to the issue. The window today extends to 4:57 p.m. Eastern Time, so we'll continue to work this issue in an effort to establish a new T0.
LC locks 2.
Go, LC.
Line rechill is complete and topping is in progress.
Roger.
LC, this is LD on channel 1.
Go LD.
Yes, sir. Please perform the contingency adjust load for hopper 60, step 17.
Roger.
This is Atlas Mission Control. The issue seems to have been caused by a bad amplifier card on a ground system hydraulic pump controller. The team is working on a solution to this issue, and again, we still have until 4:57 p.m. in this launch window, so we're working to find a solution to the issue, and we'll generate a new T0 when available. This is Atlas Mission Control. The team is working to reset the system that was anomalous. If it does return to stable, then that should resolve the issue and we should be able to generate a new T0. So while the team works that, we will just wait for them to resolve the issue. As I mentioned earlier in the show, today's AEHF-6 satellite, along with the first 5 AEHF satellites, have all been built by Lockheed Martin. Let's take a look at a video from our satellite provider to see more about the AEHF constellation.
Flight Control, LC, network.
Go ahead, this Flight Control.
Flight Control, we've been directed to load a new address file. Do you have that file ready for load?
Yes, I do.
Okay, for Operation 60, Step 170, you can give me the file name and you can proceed with load.
I'm sorry, can you say again, Launch Connect?
Yeah, I just need the address file name and then you can proceed with it.
Yeah, it's adjust_AV086_06.
Roger, 06, proceed.
LC is flight control.
Go flight control.
Step 170, contingency file adjust_AB086_06 with SDLCRC Delta Foxtrot Charlie has been verified and loaded into Dinka.
Roger. LD, LC, that one.
LD on 1.
I want to make sure you heard we have the address loaded, SDLCRC Delta Foxtrot Charlie.
Copy that, thank you.
This is Atlas Mission Control. After the hold, the launch team completed procedures to back out of the partially completed terminal count. We're waiting on resolution of the issue that caused the hold before a new launch time can be determined. After that point, we will reconduct the launch readiness poll at L-7 minutes and continue through the launch count as normal. So we'll just wait for the team to finish up resolving that issue, and we'll have a new T0 shortly.
LCM1, this is AC.
Go AC.
Ready to operate the booster hydraulic issue.
Roger. LD net 1.
LD.
MD net 1. MD. Proceed AC.
Okay, the team did a couple of troubleshooting activities to hopefully get us in position. The second one was based on some experience during the checkout of this vehicle earlier. We turned off the hydraulics and brought it back up. The parameter in question was stable, and we have positioned the engine and TR-MR valves properly. Our recommendation is to try it again.
LC concurs. LD.
LD concurs.
MD. MD concurs.
This is Atlas Mission Control. The engineering team developed a troubleshooting test that proved successful in resolving the ground hydraulics issue. So we are standing by to establish a new launch time today.
And for the team on net 1, we'll pick up operation 80 step 330 when we get new T0 direction.
LC, this is LD on 1.
Go LD.
Yes, sir. Please coordinate a new T0 of 2018.
Roger, 2018.
Good copy.
ALC, set countdown clock for new T0 at 2018. RC, please coordinate with range new 2018. Roger. OSM? OSM, LC, note 1.
OSM, go ahead.
Place the SRB ignition SNA switch in the enable position.
SRB switch in the enable position.
Locks 2, verify CISC purge flowing GN2 to the CISA.
Verified.
OSM, verify the FCO, RCO, and OSM hold fire switches are in the proceed position.
Verified.
RLM, verify red line monitor event table are in the correct configuration for terminal count. Verified. Flight control, perform launch on time verification.
Roger.
LC, ALC.
Go ALC.
Countdown clock has been set for new T0 of 20:18 Zulu.
Roger.
This is Atlas Mission Control. The launch team has coordinated a new T0 of 4:18 p.m. Eastern Time.
LCRC.
RC.
New T0 has been approved by the range.
Roger. All right, for the team, we're approaching L-8 on the L clock. T0 has been coordinated.
L-8 minutes.
Launch on time verified.
Roger. LC switch to the ready position. All personnel return to the L-7 status check, Op 60, step 210, page 129.
In a few moments, launch conductor Scott Barney will poll the launch team for the final go to pick up the countdown. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling of the launch team.
L-7 minutes.
Status check to proceed with terminal count. Atlas systems, propulsion. Go. Hydraulics. Go. Pneumatics. Go. LO2. Go. Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
ASGAS.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GCQ.
Go.
Operation support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go. Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Launch vehicle is ready to launch.
Mission director.
You have permission to launch.
ALC. Verify T0 cassette for 2018 Zulu.
Verified.
Proceeding with the count.
Polling is complete, and the launch team has given the go for launch. So again, we'll talk about what you'll hear from T-minus 4 minutes until launch. You'll be listening to Scott Barney and his team performing the final steps in the countdown procedure. You will hear the team call out that Atlas LO2 topping has been secured, followed about a minute later by the call out for transferring Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 1 minute 55 seconds, the team will command the launch sequencer to start, followed shortly by securing the Centaur LH2 and LO2 topping activity. At T-minus 1 minute 40 seconds, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed by verification of Centaur tank pressures. A final status check of Atlas, Centaur, and AEHF-6 readiness is conducted at T-minus 25 seconds. At T-minus 3 seconds, the RD-180 engine will roar to life. After liftoff, you'll hear the voice of Jesse Gonzalez providing launch vehicle ascent data. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
T-minus 4 minutes and counting. 3, 2, 1, mark. 3:55.
Ground pyros enabled.
The countdown clock has resumed, and we are go for launch at 4:18 p.m. Eastern.
T-minus 3 minutes.
Securing LO2 top.
Atlas tank flight pressure.
2 minutes, 50 seconds.
FTS internal.
T-minus 1 minute, 59 seconds.
Vehicle internal.
1:55.
Launch sequencer start.
1:50.
Securing Centaur LH2.
Securing Centaur LO2.
1:40.
Launch enabled.
1:37.
FTS armed.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
T-minus 1 minute, 20 seconds.
OCU's armed.
FCS count start.
1:15.
Reduce CCS for launch.
Roger.
1:10.
Vent valves locked.
T-minus 1 minute.
T-minus 1 minute.
Range status.
Range green.
T-minus 40 seconds.
Stable at step 3.
T-minus 28 seconds.
ECS reduced for launch.
Roger.
25 seconds.
Status check.
Go Atlas.
Go Centaur.
Go AEHF-6.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. We have ignition and liftoff of the United Launch Alliance Atlas V rocket with AEHF-6 on the first mission for the United States Space Force.
Beginning with pitch over program. Passing 15 seconds through flight. PU has gone to closed loop control. The RD-180
35 seconds into flight, Mach 1, Atlas 5 is now supersonic. Engine operating parameters look nominal. Passing 45 seconds into flight, passing through max Q, maximum dynamic pressure. The RD-180 is throttling back up to 94% as expected. Engine response looks good. Coming up on 1 minute into flight, SRB chamber pressures remain nominal at this time. The vehicle is 10 miles in altitude, 6 miles downrange, traveling at 2,300 miles per hour. "75 seconds into flight, the RD-180 is throttling to 75% thrust as expected, standing by for SRB burnout shortly. And we have burnout on all 5 SRBs. The RD-180 is being throttled back up to full thrust following SRB burnout. Standing by for SRB jettison shortly. And we have jettison of all 5 SRBs. The vehicle has gone to closed loop guidance. Passing 2 minutes into flight, the RD-180 pump speed and fuel injector pressures remain nominal. PU continues to drive mass errors towards 0. The vehicle is now 40 miles in altitude, 56 miles downrange, traveling at 5,000 miles per hour. Coming up on 2.5 minutes into flight, approximately 2 minutes left until PICO. And the RD-180 is now throttling to maintain a constant 2.5 G acceleration, and the Centaur reaction control system is now pressurizing to flight levels. Vehicle body rates remain nominal at this point in flight, and PU continues to operate nominally as well. And the vehicle is now 65 miles in altitude, 140 miles downrange, traveling at 7,500 miles per hour. Standing by for payload fairing jettison shortly. And we have good indication of payload fairing jettison. And we have Centaur forward load reactor deck jettison. PICO is in approximately 1 minute. The RD-180 is throttling back up to 95% thrust as expected. Engine response continues to look good. And the RD-180 is now throttling to maintain a constant 4.6 G acceleration limit. And we have the beginning of the boost phase chill down on the RL-10 to thermally condition the second stage engine for operation. Standing by for PICO shortly. We have the end of boost phase chill down. And we have PICO, booster engine cutoff. And we have good Atlas Centaur separation. We have indication of pre-start on the RL-10. Standing by for MES-1. And we have ignition on the RL-10. Seeing good response from RL-10 operating parameters and Centaur body rates at the beginning of the burn. Congratulations to the Aerojet Rocketdyne team, RL-10 team, as today's mission marks the flight of the 500th production RL-10 engine.
This is Atlas Mission Control at T plus 5 minutes 9 seconds. Jesse Gonzalez just confirmed the successful completion of the early phase of today's flight, and all systems continue to operate nominally. The mission is currently in the first of 3 Centaur engine burns. Our next event, Centaur main engine cutoff, will occur in approximately 6 minutes. Earlier this week, I had the opportunity to hear from General J.T. Thompson regarding the tireless work his team puts into getting national security missions in space. Let's take a look at what he had to say. General Thompson, thank you so much for joining us. What can you tell us about the launch?
Hi, Amanda. It's a really, really important launch today. Not only is it the final launch of an advanced extremely high-frequency satellite, AEHF-6, it is also the very first launch for the United States Space Force. As you know, National Security Space Launch is a team sport. And so the professionals here at the Space and Missile Systems Center who have accumulated a successful launch record of 78 over the last several years have been able to work the requirements very hard, but we do this in strong partnership with our operational launch squadrons, in this case today the 45th Space Wing and their team at Patrick Air Force Base and Cape Canaveral, but also on West Coast launches with the 30th Space Wing up at Vandenberg Air Force Base.
We're always really excited about launch, but given the current COVID-19 situation, why is it important that we launch right now?
Thanks, Amanda. That's a great question given the current world situation. There are critical things or mission essential things that the U.S. Department of Defense does every day, regardless of what the current global situation is. So even in the face of a global pandemic like the current COVID-19 crisis, we must continue to perform mission essential tasks. One of those mission essential tasks, one of those things that we have to do for the warfighter and for the United States of America is launch AEHF-6. It is designated mission essential, and it's because the AEHF constellation supports the President of the United States, other national leaders, and the joint forces with critical strategic communications around the planet. And this particular launch extends that capability out into the time frame beyond 2030. Obviously, the health and safety of our workforce is really, really critical part of that. And so while we were conducting this mission essential or critical task of this AEHF-6 launch, we've taken every precaution to ensure our workforce is safe.
What are some of the partners that utilize and help to operate this constellation?
Just like I said earlier with regard to launch being a team sport, partnerships are really, really effective in this endeavor. In fact, one of the tenets that we prioritize under our recent re-architecture called Space and Missile Systems Center 2.0 is partnership, and the AEHF-6 launch really exemplifies that concept. Obviously, the completed constellation possesses the capacity to serve all of our joint partners with the strategic terminals that they possess to be able to do protected SATCOM. So the Army, the Navy, our brothers and sisters in the Air Force, as well as a number of our international partners and allies around the planet, certainly Canada, the United Kingdom, Australia, and the Netherlands are all part of the program and very critical to the success of the program. Obviously, our industrial base has huge partnerships associated with this effort. United Launch Alliance from the rocket standpoint and from the satellite standpoint, Lockheed Martin is the prime, although Northrop Grumman provides the payload to Lockheed Martin for this important satellite that is AEHF-6.
Well, thank you for answering our questions. Is there anything else you'd like to add?
Amanda, only that I offer my hearty congratulations to this entire team that made this particular launch happen. We've talked a lot of them through some of your previous questions, but between our industrial base, United Launch Alliance, Lockheed Martin, Northrop Grumman, and many other suppliers, the partnerships that exist across the Space and Missile Systems Center between the Satellite Vehicle Program Office and the Launch Vehicle Program Office, And then across the partnerships at the 45th Space Wing and the United States Space Force, we just couldn't do it alone. And the teamwork that these folks have exemplified throughout this launch campaign has truly been remarkable. Frankly, it would be remarkable in a normal world, in a normal set of launch challenges. The fact that they have accomplished this launch and all of the work associated with it during a global pandemic that has shut down huge portions of the United States economy and many, many cities and states across the nation, I think really demonstrates that when things are at their worst, your Department of Defense and your United States Space Force are at their best.
Thank you so much for joining us today. We are now approaching main engine cutoff 1. Let's listen in to Jesse Gonzalez once again.
And coming up on MECO, we have had PU go to closed loop control, and we've had main engine cutoff. Engine cutoff pressure signatures look good. Centaur will coast for approximately 11 minutes prior to the next burn. Near the end of the first burn, we did have IIT vanish, and Centaur is now orbital. The RCS system is now commanding 100% settling and turning to the MES-2 attitude. Body rates and RCS performance looks good.
This is Atlas Mission Control at T plus 12 minutes, 28 seconds. Jesse Gonzalez just confirmed the first Centaur main engine cutoff. Our next event, main engine burn 2, will occur in approximately 10 minutes. Recently, I sat down with ULA's Julie Chittenden to discuss how thermal aspects play a role in a rocket launch and in AEHF-6 in particular. Let's take a look at our conversation. So I'm here with Julie Chittenden, and she is a thermal engineer. So Julie, can you talk a little bit about what that means and what you do?
Well, in space, it's really hostile. So as a thermal engineer, what I do is I look at all the components of the rocket and make sure they don't get too hot or too cold to function. And what's really cool is that as a thermal analyst, I get to look at the entire rocket, not just one component.
So what are some of the things we do with every rocket to mitigate the thermal impacts?
Yeah, so there are several things that we do with every rocket. One is surface coatings. It's kind of like when you have a white car and a black car outside, you can walk up to them and tell that the black car is hotter than the white car. So if there are things that are going to get too hot, we may paint them white or use some other kind of surface coating that will keep it in a certain temperature range. Other things that we can do, add insulation. We've all seen the lunar lander, and it has that gold foil part to it. That's actually insulation, and it's really lightweight. So we use something similar to that we can cover components with or other items just to make sure that they stay within a temperature balance.
A lot of our missions have a relatively short time frame between liftoff and spacecraft separation, but for this launch, the Atlas V rocket is taking the AEHF-6 satellite to a geosynchronous transfer orbit, and that's almost 6 hours from liftoff till separation. So what are some of the thermal considerations for these particularly long duration missions?
When you're in space longer, you have a much higher chance of getting too hot or too cold. So there are certain things that we can do to help mitigate that. One is if a component's getting too cold, we might put a heater on it to keep it warm during the mission. The other thing that we can do is do more passive thermal mitigations. So one thing that we do is we use what we call a barbecue roll. It's kind of like rotisserie chicken. So that's what we're doing with our stage or our vehicle, is that we'll start a roll so that one side doesn't get really, really hot because the other side will get really, really cold, and everything will be kind of out of bounds. So this way we get nice even heating and nothing gets super hot or super cold.
So do any of those launch considerations go into the actual time that we're able to launch at?
There are times where when we're looking at thermal considerations, we may say, hang on, we're in shadow like a really long time and we're getting really cold, so we might not want to launch at this day or time.
What happens when we have a decal or we paint a different color somewhere on the vehicle?
Yeah, when you see the rocket on the launch pad, you see those really nice decals on our fairing. We do account for that. We do have a white fairing for a reason, because, in Florida it's a little hot. So we like to keep things a little bit cool. But yes, we do account for those dark decals as part of our analysis. And if there were any significant changes, we'd have to go back and double check and make sure that we're okay.
So you mentioned that you look at the different amounts of time that you're going to spend in the sun versus the shadow on orbit. How does that go into affecting the actual performance of the vehicle?
Yeah, if you are in the sun for a really long time, you're pumping heat into our tanks. So we use cryogenics, which boil off at a very low temperature. So if you're pumping heat into the tank, you're boiling off your fuel. And the less fuel you have, the less time you can burn, which basically decreases the performance of the rocket. So what we do is we see how much heat goes into our tanks. We hand that off to our propulsion analysis, and they determine what that does to our performance of our vehicle.
Awesome. Well, thank you so much for talking to me today. It was great having you.
Well, thanks.
If you follow ULA on Twitter, you may have seen recently we reached out to ask, what questions do you have for rocket scientists? You asked and we answered. Here are some of the best submissions that we received. So our first Twitter question is, what makes the AEHF-6 launch special? Every launch is special, but this launch has 3 specific historical aspects to it. So first, this is our first national security launch for the U.S. Space Force. Second, this is the 6th and the final satellite in the AEHF-6 constellation, the secure military communications constellation that'll now be complete. And last, this is the 500th launch of the RL-10 that is on the Centaur upper stage. So we're really excited to launch this critical national asset for the U.S. Space Force. The next question is, how will the 411 rocket SRB configuration be different than the 551 configurations? Will a power slide be involved? You may recall for the Solar Orbiter launch last month that the Atlas V rocket used a 411 configuration with 1 SRB. So that configuration has the appearance of a power slide off of the launch pad as it clears the tower. So for today's launch, the Atlas V will be in a 551 configuration with 3 SRBs on one side and 2 on the other. So you still will have that asymmetric thrust. However, because this has much higher thrust and will come off the launch pad quicker, you probably won't notice the same amount of slide as you would for the 411 configuration. The next question is, what is the type of orbit AEHF-6 will be put into? The Atlas V rocket will deliver AEHF-6 into a high-energy geosynchronous transfer orbit. So this orbit has a higher perigee and a lower inclination than a typical GTO orbit, which is why it takes about 6 hours to complete this mission. This specific customized orbit allows the satellite to get into its geosynchronous orbit that's operational at about 22,000 miles above the Earth. We can do that in less time and with less fuel, which adds critical flexibility to this mission. The next question is, how does the second stage Centaur RCS system work? So the reaction control system on the second stage uses tiny thrusters positioned on Centaur to orient and guide the stage through space. Today's mission is the 254th launch of Centaur. Centaur uses stainless steel walls that are thinner than a dime, which was one of the key features that makes it the highest performing upper stage in the world. What are the general steps in assembling the vehicle and moving it to the launch pad? So the Atlas V rocket today and the Vulcan Centaur rocket of the future uses a clean pad concept of operations here at Cape Canaveral Space Launch Complex 41. So the different elements of the rocket, the stages, the payload, SRBs, are all assembled atop the mobile launch platform inside of the vertical integration facility, which you can see behind me. It's about 1/3 of a mile away from the center of the pad. After all of the systems have been tested, the 200-foot stack makes the journey to the center of the pad. Established on December 20th, 2019, the U.S. Space Force is a new military service that organizes, trains, and equips Space Forces in order to protect U.S. and allied interests in space and to provide space capabilities to the Joint Force. ULA's launch today of the AEHF-6 satellite is the first mission under Space Force Command. Here's a message from Tori Bruno, ULA's President and CEO, on this historic event.
I wanted to say congratulations to the newly formed United States Space Force and to say how excited we are to fly the very first mission for the Space Force. And I think it's just so apropos that it is the advanced AEHF-6 spacecraft, the sixth generation of this constellation, or the sixth satellite of this constellation, that provides secure military communications around the globe, helping to keep our troops safe, being a part of our allied presence with other countries, and being a backbone of keeping the peace here on Earth, and now also keeping the peace out in space. We are pretty excited to fly this at ULA. We care a lot about these missions. We understand them. We know how important they are, and we are all about their mission success. So now I have really just three things to say. Go Atlas, go Centaur, and go Space Force.
And we have LH2 pre-start on the RL-10.
We are now approaching main engine start 2. Let's listen in.
And we have LOX pre-start on the RL-10. We have ignition for the second burn. This burn will be approximately 6 minutes in duration, and the TDO-2 payload will be deployed shortly after MECO-2. Engine parameters look good at the beginning of the burn.
This is Atlas Mission Control at T plus 23 minutes 7 seconds. We just heard confirmation of the second main engine start. Main engine cutoff 2 is planned to occur in approximately 6 minutes. While we wait, I wanted to give our audience an update today on the progress of ULA's new rocket, the Vulcan Centaur. Over the last year, we've made steady progress towards a first flight in 2021. Last spring, we completed the System Critical Design Review and transitioned into building hardware in our factory in Decatur, Alabama. The structural test booster was completed last summer and moved to our partners at Dynetics for testing. In parallel, modifications were made to Space Launch Complex 41 here at Cape Canaveral to accommodate the larger Vulcan Centaur rocket. Those modifications included larger fuel storage tanks and increasing the capacity of the acoustic water suppression system. In the vertical integration facility, platforms were extended, and in the Spaceflight Processing and Operations Center, a second mobile launch platform was constructed to enable both Atlas V and Vulcan Centaur launches from Slick 41, an industry first. Finally, production continues in Decatur for the first 2 Vulcan Centaur flights, launching Astrobotic's Peregrine Lunar Lander and Sierra Nevada's Dream Chaser to the International Space Station. Today's mission marks the 500th flight of the Aerojet Rocketdyne RL-10 engine. Let's take a look at the history and accomplishments of this time-proven capability.
The RL-10 has been the upper stage workhorse for the United States for over 50 years because of its incredible reliability and high performance.
The launch of the Air Force's Advanced Extremely High Frequency AEHF military communication satellite aboard a United Launch Alliance Atlas V will mark a major milestone for Aerojet Rocketdyne's RL-10 upper stage engine. The RL-10 engine will be making its 500th flight, spanning over 50 years of space history.
There's not a lot of rocket engines that have 500 flights, and the RL-10 has been around for over 50 years, and it's gone through 9 major upgrades over those 50 years. It's flown on the Saturn as an upper stage, it's flown on Atlas as an upper stage, Delta as an upper stage, and it even flew on a vehicle called Delta Clipper Experimental, DCX, that was a vertical takeoff, vertical landing experimental vehicle, and one of the first engines to ever fly in a vertical takeoff, vertical landing vehicle.
The RL-10 engine began its illustrious career at the dawn of space exploration in 1963, supporting the Saturn rocket program. And from there, it was used to launch countless commercial and military satellites into orbit, sent spacecraft to every planet in our solar system, and even sent Voyager 1 and 2 on their way into interstellar space. The RL-10 engine has been the nation's premier high-performance upper-stage rocket engine for more than 55 years and has achieved an unmatched record of reliability and performance. RL-10 was the first high-performance liquid hydrogen, liquid oxygen engine ever developed.
Liquid hydrogen has a lot more energy than carbon-based fuels like kerosene, and that energy translates into the equivalent of fuel economy, which makes for a very efficient engine.
Recent advances in technology and additive manufacturing processes continue to increase the performance and quality of the RL-10, making it the perfect solution for future rocket programs like ULA's Vulcan rocket and NASA's Space Launch System that will take us back to the moon and eventually onto Mars. The Aerojet Rocketdyne team is also working on a new version of the RL-10, known as the RL-10CX, which will leverage additive manufacturing to build major components of the engine in order to make the engine much more affordable, while maintaining the outstanding performance and reliability that has made the RL-10 the upper stage engine of choice for decades.
Thanks to the RL-10 team for continuing to provide an exceptional engine that serves the needs of our nation.
Approximately 1 minute remaining in the burn, continuing to see very good performance of the PU system, and very low mass errors.
We're now approaching main engine cutoff 2, which will be followed by separation of today's aft bulkhead payload, TDO2. Let's return to the flight.
Standing by for MECO 2 shortly. And we've had MECO, main engine cutoff, standing by for TDO2 payload release in about 30 seconds. Following TDO2 release, Centaur will coast for approximately 5 hours prior to the third and final burn. And we have good indication of successful deployment of the TDO2 spacecraft from the Centaur F bulkhead carrier. We're now seeing Centaur turn to its PTC roll attitude and beginning its PTC roll, and body rate responses look good.
With TDO2 separation, I'd like to thank Jesse Gonzalez for his support of today's show. For continuing updates on today's mission during this 5.5-hour coast, the final Centaur burn, and spacecraft separation, please visit ULA's live launch updates blog at ulalaunch.com or join the conversation on Twitter and Facebook. We'll now complete today's coverage with another look at today's liftoff, which occurred at 4:18 p.m. Eastern Time. I'm Amanda Sterling, and on behalf of the entire launch team, thank you for joining us and have a great rest of the day. 5, 4, 3, 2, we have ignition and liftoff of the United Launch Alliance Atlas V rocket with AEHF-6 on the first mission for the United States Space Force.